Hello and welcome to Programming Like It's 1979. Today we are continuing Haskell for Dilettantes and we are finishing up the list module in the Data 61 NICTA FP course. I have saved what I consider the hardest for last. I don't know if this is actually hard or if I screwed myself up the last few times I did it by looking for clever solutions. So what we're doing here is we're implementing this seqOptional function, which takes a list of optionals and returns an optional of lists. So optional in Haskell speak would be the maybe data type, and list, of course, is just list. And so the example we've got here is given seqOptional a list of optionals, return an optional list. So you're kind of turning the fruit inside out, as it were. There's a couple of things to note here. One is that if we have a nil list, we're not returning empty. We're returning an optional of an empty list, which makes some degree of sense. And if there's an empty optional anywhere inside our list, then we're going to return empty. And let's just really hang a lampshade on this, right? If we were using standard Haskell syntax, what that would mean is if we have a list like that, we should return. And this is the same thing, just with different values. And if we have a list like this, return that. And I'm saying empty here. I think I mean nothing. In theory, the only thing we're really separating here, changing here, are the labels, effectively. So how are we going to do this? So I know that for almost all of this list course, I've been doing this creepy, immediately write a folder and have that handle the traversal for us. Since I know I have had problems figuring this out from first principles in the past, I'm going to actually write this with explicit recursion. My first attempt here is going to be to explicitly recurse. And that's one of the reasons I gave this its own video, was that I'm just worried that that's going to take too much time. So we'll see. Get rid of our error. So we've got a list, right, of optionals. And let's follow the types. Let's use our compiler to tell us what's going on. So obviously in this case, I expect to just be told that the whole is of type optional of list. And let's go ahead and make sure we're getting what we thought. And indeed, there it is. What's a valid fit? Well, empty is always going to be a valid fit for any optional type. So the first thing we probably want to do here is decompose this list into a head and tail, right? Because if we're going to do explicit recursion, we know we're going to need to do that. So let's get rid of that lopt, and let's create a couple bindings for item and tail. And, what you'll see if you look at Haskell code is almost always people will call these things X and XS. So that's the convention. I like giving these things longer names because that's how I roll. All right, so let's continue to follow the types here. And the only difference we should see here is that we'll have a few more reload. We'll have a few more options in our whole fits here. We see that item is of type optional A, which I think we knew. All right, so what are we going to do? Well, what can item be? Item can be either an empty. I'm going to actually move this so that it's not in my way and confusing me as I look at it. We'll put it up there. Can either be an empty, or it's going to be full of something. So let's do the empty case first, right? Keep expecting that to overwrite. It's going to be empty, and if any of these values, if any of these optionals is empty, then our whole list, our whole optional is empty. In which case we don't need this. Correct? And this is probably going to tell me that I don't have enough, I don't have exhaustive patterns. Why do I keep typing read? Oh, that actually compiles, and the reason it compiles is that we're not using those patterns. So this will really only work if the first value is empty. If the first value was just, then we'd hit that. We'd hit a runtime exception. Okay, so that part pretty easy. I think we expected that. So then our other possibility is that we have some item and we have the tail of the list. Correct? Right. And so what we kind of want to do is extract that item out of its optional container, don't at me, and append it to a list. Append it to the rest of our recursive function. Is this easier than I've always made it? I swear to you, I have spent an hour looking at this and not being able to do it. I think because I've been trying to do it with folder in the past. Well, let's see. So that would be... All right, the problem here is wrapping this entire thing in an optional. Right? Because if we do this, which is kind of like the direction I'm going in, if we do that, then what we end up with is not an optional. This yields a list, but does not yield an optional. How do we get this into an optional, inside an optional? Well, I know this isn't going to type check, but let's compile it anyway and see if the types lead us anywhere. Could it match? Okay, so yeah. In the expression item, seqOptional takes a list of optionals and returns an optional list. All right. In the second argument of cons, namely seqOptional tail, so the type of seqOptional tail is our optional of some list. This is actually the correct type, right? Can we use map or fmap? Have we defined map or fmap? Let's look at optional. I think we have map optional, right? Given some function from A to B and some optional A, return optional B. That transformation kind of looks like what we actually want right there. Right? Given, is that, will that work? Right, and that's our function, and that's our A. Type checked. Okay, well, we actually passed, well, we passed the empty test. That's not at all helpful. Non-exhaustive patterns. Okay. Why is this a non-exhaustive pattern? I thought This covered all the cases. Did I forget to save it? No. What pattern am I missing? Oh, if there's a, literally, we're missing this. And that needs to be full nil. Oh, for our various flat maps. You know what? I'm going to remove some of those flat map implementations from before, just so they stop giving me yes, I'm being very type A. What can I tell you? All right. And that worked. I know this is silly. I know this is very, there's no reason to do this. There's no reason to think that this won't work. The test just passed, but I want to see it. Huh. So now why, I mean, this was a little more involved than most of the earlier exercises or the other exercises. I think this is actually more involved than the ones that came after it, even if I had tried to do this via fmap. And I think the reason for that is this, the use of map. I don't think we use map, certainly not map optional, anywhere else here. But it's not awful. So here's an example where, in order to solve this problem, my dumb brain needed to step down a level. And so there's always this, and I view things like folder as abstractions, right? You're abstracting over the process of recursion. But abstraction can be confusing, at least to me sometimes. And so here's a very concrete example where if I had started this exercise by doing folder, I don't think I would have gotten to the realization that I need to use map optional, because it would be kind of wrapped up inside this lambda. And in some sense, that's very puerile, you know, like it's just wrapped a different way. But it turns out that cognitively, it's easier for me, at least, to see it this way. And maybe this is something where if I was not a dilettante, if I wrote a lot more Haskell, the solution would be obvious to me. So looking at the solutions provided by Tony Morris for this class, his implementation of this, can I just paste this? I think I have it in the ring. No. Is this. Fold right, twice optional of cons, providing full nil as the accumulator. The full nil part makes sense because that does directly correspond to our base case for our recursional. What is twice optional? Twice optional is apply optional. The chances that I would ever figure out this solution seems like nil to me. Oh, sorry, seems impossible to me. Well, first of all, let's make sure that this actually type checks. I'm sure it does. It's the official quote-unquote solution. All right. It sure works. What if, okay, so my question is, this use of twice optional, what does twice optional even mean? Like looking at this function, given a function that takes two arguments and returns a third, and two optionals return a third optional. I mean, I can't even really explain it. Let's see if we would we find this? Maybe the compiler would suggest it. Let's pretend we wrote fold right and we're following the types. Found a hole. A and an optional yields an optional. Valid hole fits include sequence, A to B to B, seqOptional 2, well, that's ourselves. No, I mean, I would not, my brain is so poisoned, and maybe this is an example of my inability to see the forest for the trees, right? So if we look at right, so the idea is, I think, no, I don't get it. Well, let's continue filling in that hole, right? Maybe we would get further. Maybe we'd get here, right? That's a standard way. You know, you can do a lambda of some sort. Hole is optional list T. Yeah, I don't get it. I would love for one of my viewers who understands what's going on here better than I do to explain, let me back up, explain how I would arrive at this solution, right? If I step through, I could, type check this and see that, yes, it does fit the hole. I believe that this is the solution. I don't understand how an earthling gets to that solution. And I think this type of thing is where a lot of people struggle with Haskell. People say, just follow the types. And a lot of times when you do that, what happens is you end up with, and you're going to see this a lot when we get to functor and the various lift functions and monad, you're going to see cases where I guarantee you I am going to get to the right solution by following the types one at a time and cannot explain to you why my solution works other than, well, I followed the types that the compiler errors were telling me to. This case, I don't even see how that's done. So this has really this really leaves me bamboozled, and I would love some help in explaining how should I have gotten to this fold solution. This one, I feel like I've convinced myself that, yeah, all right, I got there a step at a time and it wasn't that bad. This one completely befuddles me. Well, I did promise you that we were going to continue to get more and more abstract, and that is going to happen in our next episode of Haskell for Dilettantes, because we're covering our first type class that I think we've touched on these a little bit, but we haven't actually implemented a type class from beginning to end, and we're going to do that with the functor type class. And we'll talk more about what a functor is. Quick one-sentence preview. A functor is the type class that implements the map operation, or that defines the map operation. So we're going to be looking at that next time. I'm really glad you joined me. I know that most of my videos are me making mistakes and talking about them, and this one feels like it was all me talking about my mistakes. So I hope this makes for interesting YouTube. I would love to hear your comments. Please leave them, and we'd love to have you like, subscribe, and or become channel members. You've been watching Tea Leaves Programming. We're programming like it's 1979. Doing Haskell for Dilettantes. Thanks for watching.